Welcome to example number 6. This question is about the electric field and the motion of an electron that is orbiting a hydrogen atom. In the Bohr model, the hydrogen atom, when the atom is in the lowest energy state, the distance that the proton is from the electron is given as 5.29 times 10 to the power negative 11 meters. So this is what we would call in our given, I guess, our R distance. So 5.29 times 10 to the power negative 11 meters. In part A, we're asked to calculate the electric field at that distance of 5.29 times 10 to the power negative 11 from the point charge, which is the proton. This is the proton, by the way. So one thing that's not given in the problem, I guess you have to realize, is that the charge of a proton, often people surprisingly confuse this, is the same as the charge of an electron, except it's positive. So it's positive E, that's the symbol we use for the charge of an electron. So it's positive 1.60 times 10 to the power negative 19 coulombs. So to calculate the electric field for this point charge, we're going to be using the formula we just developed in the electric field for point charges, which is E equals K times the absolute value of Q divided by R squared. And now we substitute in, and we get the following. And then putting it into your calculator, you'll get 5.14 times 10 to the power 11 newtons per coulomb. So now calculate the magnitude of the electric force. I guess we could have done B before A. It really doesn't matter. And there's a couple ways to do B. You could calculate the force on the electron, which is really Coulomb's law. K times Q of the electron, and then Q of the proton, divided by the distance squared. Or alternatively, you could use, since you've already calculated the electric field, you could use F equals Q times E. This is Q of the electron. And since we're looking for the magnitude, we'll just simply take absolute value signs around the charge of electron. Let's do it the simpler way here. So this force would be the charge of an electron, the absolute value of that, which is 1.6, negative 1.6 times 10 to the power negative 19 coulombs. But when you take the absolute value of that, you're going to get a positive answer. And then multiply by the electric field strength of 5.14 times 10 to the power 11 newtons per coulomb. And you'll get a force of 8.22 times 10 to the power negative 8 newtons. Okay, now part C is to bring in something you learned earlier last semester. This is assumed to be moving in a circular orbit. So how fast is the electron if it were in a perfect circular orbit around the proton? Hopefully you remember Newton's second law applied for circular motion. Sum of F equals mac. That's the centripetal acceleration. The force that's causing it to accelerate towards the center is this force of 8.22 times 10 to the power of negative 8 newtons. And then this is the mass of an electron times the velocity of it squared divided by the radius. So this velocity would be 8.22 times 10 to the power negative 8 newtons. That's the force. Multiplied by the radius of orbit, which is 5.29 times 10 to the power negative 11 meters. And then we're going to be dividing by the mass of an electron, and that is, hopefully you recall, 9.11 times 10 to the power negative 31 kilograms. And put that into your calculator, and you'll get a rather fast velocity of 2.18 times 10 to the power of 6 meters per second. And that's it for this example.